And these approaches, there's a number of them. I'll just highlight a few of them here today. On the left, companies start with a single die. So this is just a screen capture of the Google Sycamore processor. The challenge with single dies is that as you make the qubit count larger, your yield requirements really increase quadratically, right? Because then you double the number of qubits, but then you need to increase if you don't want to lose more than 1 qubit per die, then you have to increase your yield. And that is very challenging to do. And you're likely going to need over 99% or higher to yield these chips at a sufficient scale that you can use them. Because when you have a dropout in a quantum processor, it really impacts the algorithm and the power of that computation. And so we're seeing a limitation by Google and IBM around 100. One way to tackle that is with multi-chip dies. So then you have smaller individual dies, let's say it's 40 to 100 to 200 qubits that you can manufacture with high yield, but then you're actually placing them on some sort of carrier wafer and bonding them together. Here's a picture of Rigetti's Aspen multi-chip. And then that way, if you have a strong coherent connection between all the neighboring qubits, as you're lacing those together, connecting those together, if you have low loss, and low coupling and overhead, then you can actually make a very powerful processor if you have high enough fidelities to use that full chip. These multi-chips are likely going to be limited to around 1,000 qubits per multi-chip die. Maybe they could get up towards closer to a couple thousand or 10,000 max, but really limited by the size of the cryostat. And then how many of those multi-chips are you going to bond together? Those kind of daughter boards do you bond together? And so really where we believe the field is going is that you're going to need to network together QPU chips to then have as many multi-chip dies as you can in a cryostat, but then have the optical interconnects. And the limitation there is going to be the fidelity of that entanglement between the different QPUs. You're going to have to likely do some transduction, most of them, unless you're operating at the telco wavelength, which is very beneficial. And so what is the fidelity of that entanglement? What is the lifetime, the coherence of that entanglement? And how distant can they be? So those would be some of the key factors that we'll be looking at there.